A person drops a stone down a deep well and hears the echo 9.7 seconds later. If it takes 0.9 seconds for the echo to travel up the well, how deep is the well? And what is the speed of sound in the well? So, we know that the total time minus the time for the echo to come back up is equal to the time of the fall, since the total time is including the echo, and the echo time is actually not part of the fall. So really we just need to plug our given values in. Total time of 9.7 seconds and the echo of 0.9 seconds, which gives you 8.8 seconds for the time of fall. So now we have a kinematic equation which says that the displacement of an object is equal to its initial velocity times a time interval that passes plus 1/2 times the acceleration of that object times the time interval squared. And this can actually be used to help us calculate the height of the well. In this case, it's really changing the y direction or the vertical direction, but this change in x, or the object's displacement, the stone's displacement, is actually the height it falls down to the well before it hits the bottom of the well. And it has no initial velocity because a person just drops the stone. He doesn't throw the stone down. So that is simply equal to 1/2 times the acceleration times the time interval squared, where the acceleration is equal to g. And note that in this coordinate system, I'm setting the positive x direction to be downward because that's our only object, and it would actually simplify our calculations to just set it to be positive instead of negative. So we can say that the height of the well is given by 1/2. The acceleration is the gravitational acceleration, and gt squared. So we know the time, where the time is the time of fall, and g is the gravitational acceleration of 9.8 meters per second squared. So this becomes 1/2 times the gravitational acceleration of 9.8 times the time it takes for the object to fall, which is 8.8 seconds squared. So now this should give you about 379 meters. So the height of the well is 379 meters. Height of the well, 379 meters, which is pretty tall. Okay, now it asks us to calculate the speed of sound in the well. So we have we can use the same kinematic equation, except this time we're using it for sound. So the displacement, which again is the height, is equal to the velocity. The initial velocity of the sound is, the sound usually travels at, we're assuming the sound travels at the same velocity as it starts and throughout the well. So its initial velocity is really just the speed of sound. So this is going to be the speed of sound. And we have times the time interval. And of course, the sound does not accelerate as it propagates. So we can rearrange this to say that the speed of sound is equal to the height divided by the time, where the time is the time of the echo. It's the time for the echo to come from the bottom of the well back up to the person. So plugging everything in, the speed of sound is equal to 379 meters divided by 0.9 seconds it takes for the echo. This gives you 421 meters per second. So that's our speed of sound. So you have that the speed of sound is equal to 421 meters per second. And that is how we would solve our problem here. And just a quick note, this is just the speed of sound in the well.